Recording is rolling. It is Thursday, January 30. So I have a couple of Doppler demos for you guys, a live demo and also a Paul Hewitt video to run that. And then the main focus today is going to be these chapter 14 and 15 puzzles. Okay? So we're going to do these the same way we did the last section, which is I'll give you guys most of the class to work on these. As long as you're working on them in that time, then I'll give you guys the credit in the grade book. And then for all the students who are absent, they can just turn in their work on Monday, and then I'll award points then. But as long as you're working on them in class, then you get points that way. Because at the end of class today, I'll get you guys your take-home quiz. So you guys can work on that for a few days, and that'll be due on Monday. Right? You guys got that in your planner? Take-home quiz due Monday, right? Which you don't have right now, because I'll give it to you guys the last couple of minutes of class, right? And then tell you guys what we're doing tomorrow is tomorrow is going to be all Doppler puzzles. So today I have, of course, the Doppler demos for you guys. Actually, one of these puzzles is a Doppler question. It's chapter 15, number 68. I'll solve that one with you guys. And then tomorrow it's going to be all Doppler tomorrow. Right? So you guys good with what we're doing? Right. Before I dive into those demos, got a couple extra things too. So you guys remember tonight is the STEM career showcase. That's science, technology, engineering, and math. This is at 6 o'clock in the cafeteria. Says connect with UCF, Boeing, Brevard Zoo, Collins Aerospace, and more. So if that's interesting to you, that's tonight, 6 o'clock, cafeteria. Something else I got going on is Drop Savers poster contest from Cocoa Utilities Department. This I posted to Google Classroom, I think 2 days ago. Google Classroom, 2 days ago. If you want to download this, you can read all the details. But it's a poster contest. And one of the categories is for high school students, so grades 9, 10, 11, 12. And what's going on? So prizes. So if your poster is award-winning poster, then I think all three of these you get, I think. It says receive certificate of participation from Cocoa Utilities Department, display of your artwork in City Hall and Cocoa publication and social media, $25 gift card. So if that looks good to you, if you want to make a poster, it has to do with saving water, then you can download this from Google Classroom and do that. All right, so I have a demo for you guys. I have a little piezo right here, a piezo. I'm going to tape that to a battery that's inside, well, all this soft yarn right here. So see if we get this to work. Yeah, this might take you a couple of times. All right, I think it's working. Can you guys hear a tone? It's like, all right, well, whatever microphone's picking this up. All right, so that's a solid tone, right? Now what I'll do, all right, so I'm gonna, oh, look, it's on a string here. I'm gonna wing this around in a circle over my head, like a horizontal circle. All right, now you guys listen. Do you guys hear a rising and falling pitch? It's going up, down, up, down. Yeah, I see you guys saying yes. Now I have to take your word for it because I'm at the center of the circle. So guess what I hear? I just hear a solid tone. Yeah, so I don't hear any change at all. I just hear a solid. So to me, that whole process, nothing ever changed at all. Just sounded the same. Okay. And that's called the what effect? Doppler. All right, let's get some Paul Hewitt.
When you're like a bird, you're looking right down in the water, and there's a bug sitting there. And this is a lake that's perfectly smooth. But now what the bug starts to do is the bug starts to jiggle up and down. And when that bug jiggles up and down, that bug is a vibration, yeah? And that's vibrating on a nice surface, yeah? We're going to make what? Begin with a W. All right, all right. We're going to make waves, gang. We're going to make waves, okay? And the waves kind of look like this. Where I draw the line, that represents like the crest of a wave, like it might sort of be like this. You kind of see what I'm saying? Okay, so this represents the crest of the waves. And the waves go out in all directions. And the fact that they're circles is kind of evidence that they go out in all directions at the same speed. Isn't that true? Like if it went faster over here, then the wave would sort of be like that, yeah? Okay, so the circles are evidence of the same speed. Okay, now what would be the frequency of the waves compared to the frequency of the vibrating bug? In other words, if you put your hand here, blip, 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 the waves would hit your hand, yeah? Certain frequency. How would that blip, blip, blip compared to the whoop, whoop, whoop of the bug? Same. Isn't that right? The frequency of a wave is the same as the frequency of the vibrating source. Makes sense, doesn't it? Let's suppose now that the bug swims in this direction. What the bug is going to do is the bug is going to swim in the direction of the waves that it's producing, and it continues to vibrate a little bit, yeah? Wouldn't the wave pattern look something like this? Can you be seeing that? In fact, what direction would the bugs be swimming, gang? I mean, you can tell it's going that way, right? Well, the bug might be at rest and the water's going this way. I mean, motion is relative anyway, yeah? Okay, now if I put my hand over here, would I get a higher speed wave, a lower speed wave, or the same speed wave? Check your neighbor. And make sure you're listening to the question that's being asked.
Because the question you just asked is kind of a trick question. So see what you guys think. So he said he puts his hand on the right side, right? The bug's swimming towards him. He's feeling the waves bounce out of it. You guys know all those circles could be like the crest of the waves going blip, 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 right? So because the bug's swimming towards him, the speed of those ripple waves hitting his hand, is that faster than, slower than, or the same speed as before? Same? You guys saying same? Same? Everybody saying same? Yeah. All right. You guys are on. That is true. Guys, once that ripple wave has been released into the medium, in this case, water, or later on we'll do air if there's like a car driving, whatever, that wave goes at whatever speed it goes through that medium, regardless of the motion of the source. So independent of the motion of the source. Now, something else changes. Guys, the speed doesn't change. You guys just said that. What changes? The observed. The what? Ooh, starts with an F. Frequency. The frequency that the waves. All right. So same speed, different frequency. Ooh, a different wavelength for that matter, right?
Question that's being asked. How many people say, hey, the speed of the wave is going to be the same? Yeah, that's right. The speed of the wave doesn't change. What does change, guys? How frequently that wave encounters you is different, yeah? So I can get a different frequency. When I put my hand here, higher frequency or lower? You see it? Over here. Bloop, bloop, bloop. That change in frequency due to motion of the source or the receiver is what we call the, named after a person. Okay, good.
Yeah, Doppler effect he's looking at, right? Doppler effect. All right, so this is a question I'm going to guide you guys through today, right? Is one of these Doppler ones. And of course, that's going to be our main focus tomorrow. All day tomorrow, we'll just focus full on Doppler, right? But set this up today, so you guys can think about this for a time. All right, so, I'm definitely see a car in motion. Here's an observer here. So I got a source, which is the car, and the observer, right? So maybe the car's blaring a horn, beep, beep, or something like that. Right, you guys ever stand by the sidewalk here? Right. So the frequency that you observe from that source, well, it depends if that source is headed towards you or away from you, right? Now here's the full formula. Now I see frequency observed here and the source frequency here. Say the car's blaring its horn. It's like, I don't know, 400 hertz. Like beep, 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 beep. Suppose that's like 400 hertz, right? Let's start with this. Guys, if this car is parked and the observer is just standing still, then what is the observer here? Is the observer here also 400 hertz? So the observed frequency matches the source frequency? Is that what you're? And that would be the entire story. If the car is parked and the observer is standing still, everybody agrees on the frequency, right? But if you put one or both of these guys in motion, now the rest of this equation pops up, right? And I want you guys to see logically that this makes sense. Guys, everybody full focus up here? Everybody looking? Right? See, this makes sense. Actually, here, to pick up from that last story I just said, if the velocity of the observer is 0 because he's just standing there, and the source velocity is also 0 because the car is parked, right? Guys, what is the speed of sound divided by the speed of sound? What is that fraction equal to? 1. Yeah, anything times 1 is just itself. Okay, so it still matches, right? Let's do this. Let's say, let's have the car parked. I know my picture doesn't match that, but can you guys imagine the car's parked? Let's have the observer running towards the car. Yeah. Running towards the car. Guys, if you're running towards the car, let's start from the end result. Should you perceive a frequency that's higher than or lower than the actual source frequency? A little bit higher, Yeah, right. So if you figure that, that makes sense, right? Right. If you have that in place, that'll tell you how to navigate this plus or minus right here. Because I have the car parked, so the source frequency is zero, so I can ignore that. Right? But what should you do now? Let's say he's running towards it like Usain Bolt, like as fast as he can. So get pretty good velocity going here. Should you do plus or minus right here, running towards the car? How many guys say plus? Who says plus? Plus? Yeah, yeah. Okay. Because guys, if you do plus on top, doesn't that make the overall numerator larger? Which makes the overall fraction larger. Ah, so the observed frequency is larger than the source frequency. So if the source frequency is like 400 hertz, like beep, beep, the observed frequency, like beep, beep, has to be a little higher than that. Ooh, maybe like 500 hertz, 400 hertz, 500 hertz. Ooh, right? Right? Right. What if this guy's running away from the car? Running away from the car. What should you do on top, plus or minus? Minus. Ah. So if the car's beeping like beep, beep, maybe you hear like beep, beep. So if this is 400 hertz, maybe this is 300 hertz. Ooh, right? Yeah, depending on the numbers. Okay. All right. All right. You guys ready for a trick here? Because the motion of the car might be a little trickier to think about. Let's have this guy just standing at rest, just to keep all else equal. So the velocity of the observer could be zero. I could just get rid of this bit right here. He's just standing there. Here comes the car. Beep, beep. Car's driving towards this guy. Now, guys, driving towards, should the observed frequency be larger than or less than the actual source frequency? Like, guys, if the source frequency, here, guys, everybody following here? Yeah, you have to think deeply on this, and then everything else. Tomorrow's going to be a lot easier if you're thinking really deeply on this right now. If the source frequency was 400 hertz, does this guy hear more than or less than 400 hertz? More than, if the car's driving for him. So if this is like beep, beep, if you're inside the car, you hear beep, beep. Outside the car, you beep, beep. You hear a higher frequency if it's headed towards you. Okay. All right. Now let's navigate this equation. How are we going to get from 400 hertz to 500 hertz? Does this overall fraction have to be more than or less than 1? More than 1. Okay. And the observer's just standing there, so this bit's 0. Okay. So how are you going to make this fraction more than 1? Do you add or subtract on the bottom? Subtract. Do you guys see subtract? Right? Because if the car was parked, V sound over V sound, that's equal to 1. Right? Then if you subtract on the bottom, that makes the denominator small, which makes the overall fraction bigger, hence bigger than 1. Ah, and that would match the situation, wouldn't it? Right? All right. So one more scenario. What if the car's driving away from the person, which my picture doesn't show, but make believe. What if the car's driving away? Right? Does this person hear a high or a low frequency? Low, really low. Like inside the car, it's beep, beep. Outside, beep, beep. That sounds lower. Okay? So in terms of numbers, if the actual source frequency was like 400 hertz, maybe you only hear 300 hertz. Ooh, that'd be like a lower tone. Right? So how do you get lower? Should you add or subtract on the bottom? Add. It has to be add. Do you see that? Right. Now put it all together. What if the observer is in motion and also the car is in motion? Ooh, well, now you can navigate with the book. Actually, that's where we're headed next. Right, so I'm going to solve one of these with you guys today. Chapter 14 is vibrations and sound. Chapter 15, vibrations and waves. And chapter 15 is specifically sound, which is, of course, is a type of wave. It's a longitudinal wave. Okay? Number 68. You guys see number 68? A fire truck. The number 68. Okay. The rest of these, I'll let you guys work on it independently, and of course, help you out if you have any specific questions. But okay. This one I'll guide you guys along. Okay. And then tomorrow you're going to get a bunch of puzzles that look a lot like this one. Okay. So let's get a road going. Get a fire truck. What does a fire truck look like? I guess he's got a little fire ladder right here. Okay. Got little fire truck wheels. And then he's traveling at velocity equal to 35 meters per second. Ooh, that's zipping along. That's like interstate highway speed right there. Catching up to a car. There's a car in front of the truck that's also traveling the same direction, but slower. So the truck's catching up to the car. Okay. This car is going 15 meters per second. Right? Right. This fire truck is blaring a siren. So if I draw on the crest of waves, I bet it's going to match my poster. You think it looks something like that, right? Where you got like crest, 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 and behind it's like crest, 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 right? Okay. Now make sure you guys are following, because once those siren waves have left the truck and they're just traveling through the air, Is the speed of sound the same in all directions? Yep, I bet it's about 340 meters per second, which you guys found yesterday in your speed of sound lab. That's what you guys saw yesterday. Actually, that's the number we're going to need too. Let me go ahead and jot that down. Speed of sound, because the textbook question does not explicitly spell that out, but you need to make a reasonable guess. Right now, it depends on the temperature and the pressure. They don't say, are you sea level? Are you in Colorado? Is it winter? Is it summer? So we're just going to guess maybe 340 meters per second. This it could be a nice round number for that, right? All right. So, and that speed is the same. It has nothing to do with the motion of the truck. The speed of sound, once it's released through the medium of the air, it is what it is, right? But the observed frequency, guys, if you're sitting in this car and the siren is catching up to you, ooh, I bet you hear a high pitch, and when it passes, maybe lower. So, maybe something like that. Right? So we're going to give it a solid source frequency of 327 hertz. So I'll say F source. So if you're either inside the fire truck or if the fire truck was parked, it would sound like 327 hertz. Right? I think yesterday I played you guys 220 hertz. So it used to be a higher pitch than that. Okay? All right. What frequency is heard by the driver in the car? So I'm going to set up my Doppler equation. So the observed frequency is equal to the source frequency. Again, if nobody's moving, that's the entire story. But if there is motion, and there definitely is motion here, I need to multiply and set up a ratio. The speed of sound shows up here and also here. Speed of sound, top and bottom. I got a plus or minus. Okay? And then velocity observer, velocity source. Now the observer is, we'll call it the car, and the source we'll call it the fire truck. Sure? Because you're sitting in the car, you're listening, and the fire truck's blaring. Okay. All right. So let's get some numbers here. Observed frequency, that's the question. What's the observed frequency? The source frequency is how many hertz? 327. Got 327 hertz right there. Right. Multiply that by, right? Set up a ratio. Right. Well, speed of sound, we're just calling 340 because that's a reasonable guess. It's probably about 340 meters per second. Right. And if you want to use a different number, maybe you could say, like, what if it was like 350 or 330? And you can play around with it. I don't think the answer would change that much. Okay. Here, I'll write in the speed values for observer source. Like I know the car's going 15 meters per second and the truck's going 35 meters per second. Okay? But to really finish this, you got to figure out what's plus or minus. Like, is this plus or minus and is this a plus or minus? Because it's only one of them, right? All right, so let's go through this again. Let's start with the car, right? We'll look at the car in isolation. So ignoring the motion of the truck, I see the car is trying to get away from the truck. Right? So the fact that the car is trying to get away from the truck, should I add or subtract on top? Subtract. Yeah, right away. Right? Because again, in isolation, all else equal, that would decrease the numerator, which would decrease the overall fraction, which would give you a lower pitch. That would be true if you're trying to run away from something. You perceive a lower pitch. Okay. Now let's bring in the truck. Okay, so we're going to ignore the car and say, well, the fact that the truck is headed towards the car. Ooh. Should you add or subtract on the bottom? Let's think back a bit. So I remember, here, you guys remember this, right? So if the source is headed towards the observer, do you perceive that as a higher or lower pitch? Higher pitch. And how do you get a higher pitch? This overall ratio should be what? More than or less than 1? More than 1, right? And if the effects come from the source, then the only way to blow up this fraction big is for the denominator to be very what? Big or small? Small. So you have to do what down here? Subtract, right? You guys see that whole logical process, right? So these are both minus. It's minus. They're both minus, right? Okay. Now, that whole process I walked you through is, really like a logical way to figure this out, which I do every time I solve one of these Doppler questions. And tomorrow you're going to get a bunch of Doppler questions. So you got to answer those questions over and over. Right? Now, some textbooks actually approach this differently. They'll say, well, do you guys see that the car and the truck are moving in the same direction? Right? They're both moving to the right. Right? Do you guys see that these signs also match each other? Minus in this case. Some textbooks actually start from that to say, okay, well, if you know the directions of these things, then we'll define this as a minus, and we'll define this as a minus, and okay, it's good. And the fact that they're both in the same direction, the signs have to match, right? Anyway, it's calculator time. So calculator, make sure, of course, you can correctly communicate this into your calculator. Order of operations, you can group with parentheses, the whole deal. Make sure you're getting a reasonable number. Guys, even before I type anything in, a reasonable number should be, because what would be more reasonable? Let's say 250 hertz or 350 hertz. What sounds better? 350, right? Because you guys see overall the truck is catching up to the car. So I think the answer has to be more than the source frequency. So I think 350 is better than 250. Right? What sounds better? 350 or 3,500? Probably 350, because right, it can't be like super crazy, right? So yeah, think what's a reasonable order of magnitude, right? I don't think it's like going up by a whole octave, right? So 327 times, and then 340 minus 15 in parentheses, then divide by new parentheses, 340 minus 35. And oh, it's 348. Yeah, that's right in line with what we were thinking would be a reasonable answer too, isn't it? 348 hertz. All right, so I'll go with that. You guys go with 348 hertz. You guys good? All right. All right, so I got another poster for you guys though, because is it possible the source could be outpacing the very sound waves that it's sending out? Can you travel faster than the speed of sound? Yeah. Right? In fact, if you're traveling twice the speed of sound, that's called Mach what? Mach 2. If you're traveling 3 times the speed of sound, would that be Mach 3? Yeah, so Mach whatever is your speed compared to the speed of sound. You divide it, right? Oh, that's called supersonic. Super greater than sonic sound, greater than faster than sound, right? And do you guys see all these? Yeah, these circles might represent wave crests or maybe a high pressure point since we're talking about a sound wave, right? Do you guys see that overall it makes like a cone shape, right? And I got a video for you guys to see that too. So if you're standing here observing, right, say if this is a rocket goes overhead, right? Do you hear it yet? Right here, do you hear it yet? No, because none of these sound waves reach you. But when they do, they hit you all at once, pow, and you hear a what? Sonic boom. That is a sonic boom. All right. So I got some supersonic going on here. All right, let's check this out. Got some supersonic jets. And some of these frames you can see a cone wave. Ooh, do you guys see kind of a flat cone right there? All right, let's see. Oh, yeah, there's definitely, well, you have to think in 3 dimensions. That would definitely be cones, wouldn't it? Right? In fact, if you knew the angle of that cone, if you like broke out a protractor, do you think you could actually calculate the speed of the jet to produce maybe that geometry, right? You could do that. There's an equation for that. We're not going to apply it in class, but just in principle. Oh, there's a nice cone right there. You guys see it? Nice. It's kind of a flat cone. So, actually, that's a little steeper cone right there. So maybe that plane's going just a little bit more than the speed of sound if it's pretty flat, right? All right. So, back over here. All right. Just real flat. Yeah, real quick, I'll flash through some other posters. Okay. So you might need speed equals wavelength times frequency today. I bet that could be pretty handy. If you get some oscillating scenarios, here's a mass on a spring, the time period, that's the lab you guys did recently. Right? And then a lab about a week ago involved, well, the pendulum version of that. It's got time period is 2 pi square root over g. Right? I'll send you graphs so that helps. Where's, all right, got it. Yeah, classic pendulum here. All right. So, you know what's might be helpful for some of these? I know there's a Hooke's law question on here. There's some Hooke's law. You guys remember F equals kx for Hooke's law? Now, if it's energy in a spring, guys, what's the formula for energy in a spring? 1/2 kx squared, right? I think that pops up somewhere. There's some questions about echoing. Guys, do you guys know the equation distance equals speed times time? I think it's one of the first things we ever did, right? Actually, you probably knew that before you ever stepped foot in this classroom. Distance equals speed times time, right? Oh, how about this? Guys, if a wave echoes off a canyon wall, that's one of the questions. Echoes off a canyon wall, right? And you're counting the time delay, right? Isn't it true the wave has to travel across the canyon and also back? So it's like twice the width of the canyon, right? So there's a little critical thinking questions like that, right? But here's the way we do this. Same way we did this last time is as long as you guys are working on your 1450 puzzles this class period, I'll go ahead and put the points in. For any absent students, they can turn in their work on Monday, and then I'll give credit for that. And at the end of class today, the last couple minutes, I will get you guys your next take-home quiz. The next take-home quiz is due when? On Monday. Oh, yeah.